Let's talk about bimolecular elimination reactions, also known as E2 reactions. Much like an SN2 reaction, in an E2 reaction, you have a bimolecular process that is um, involved at the transition state, the rate determining step of the reaction. So you have a rate law that is bimolecular, hence the number 2 in the abbreviation. The other thing too that an E2 reaction bears in common with an SN2 reaction is that the entropy of the activation energy, or excuse me, the entropy of the transition state is negative. And this tells us that the transition state is more ordered. And one way to make this happen is to bring the two reactants closer together at the rate determining step. And that's to say that your base will be in the process of attacking the proton, which is one carbon over from that which has the leaving group present on it. And the idea is that when you remove this proton, the electrons of the alpha carbon, the one that's next to the carbon bearing the leaving group, the electrons will come over to form that double bond, and in the process you'll kick out the leaving group. But in the transition state, what basically happens is that the base approaches and gets close enough to the molecule to start forming that conjugate acid, YH bond, all the while having that carbon H bond beginning to break, your double bond beginning to form, and this leaving group beginning to come out. So all of that is kind of happening at once. And this kind of creates a more orderly state that is emphasized by the negative delta S double dagger of the Irene-Polanyi equation. All right, so technically all at once, you end up producing your conjugate acid, you end up producing your alkene, and you end up producing your leaving group, right, as an anion. So the attack, now this is very important, the attack for an elimination has to happen on the neighboring carbon, also known as the alpha carbon of the molecule. And the alpha carbon of the molecule, well, actually, this is the alpha carbon, this is the beta carbon, so let's get that straight. So you attack on the beta carbon, specifically the hydrogen. So if this beta carbon does not bear any hydrogens, you cannot do eliminations. So you must have at least one hydrogen, on the beta position in respect to the leaving group in order to undergo an elimination. All right, so let's do an example to see, first of all, how to predict if a reaction is going to be an elimination or not, and then we'll do the entire analysis of the E2 reaction. So notice here that we have first of all, a leaving group, the bromo group. This happens to be a secondary alkyl halide. The other thing that we notice is that the potential nucleophile is also a strong base. Okay, so that should kind of raise a few pointers. Whenever you start using strong bases, and we're talking bases that are even stronger than hydroxide, but hydroxide could do the trick as well, since that's also a strong base. Whenever we use strong bases, you should already be on the lookout for potentially doing elimination reactions. That's a big hint. The second thing is that we are hitting the reaction. Okay, so the combination of having a strong base and the fact that we're hitting a reaction, this is a dead giveaway that an elimination is going to happen. And this is to be contrasted with your SN2 reactions, where if you were to use a strong base, you gotta make sure that the temperature is at the very most room temperature, ideally less than that. And of course, the final prerequisite is that in addition to having that leaving group, you have hydrogens on the positions next door, the alpha positions or beta. It really depends how you want to look at it. In the PowerPoint, I'm going to refer to them as alphas. So having those alpha hydrogens next to your leaving group, using a strong base and heating, this all spells out elimination, and specifically a bimolecular elimination reaction, or E2. Okay, now the way this is going to play out, because both the base and the leaving group are going to interact at the transition state, at the same time is that you have to arrange the molecule in an anti-periplanar conformation. And what that is to say is that the CH bond has to line up exactly opposite of the bond of the carbon to the leaving group. So in this case, the CBr bond. In order to really tell how that's going to look, we have to consider the two alpha hydrogens in this molecule, and specifically we have to look at the Neumann projections. So looking through this bond, so this will be the carbon in the front and this will be the carbon on the back. This carbon has two hydrogens, so you're going to have hydrogen, hydrogen, and methyl. And then you have, here's where you have to be very careful because you have the stereochemistry to consider. You have bromine sticking out, hydrogen going to the back, and then you have the sec-butyl on top. So notice that on top we have the sec-butyl. Since the bromine is sticking out towards us and the point of view is here from the left side, the bromine is going to be pointing to the right side in the Neumann projection. All right, so what I mean by being anti-periplanar is that the CH bond of the, in this case, the front portion of the Neumann projection has to be directly across or on the opposite end of the carbon Br bond on the back side of the Neumann projection. So right here, this is already kind of good, but this is not the only hydrogen in the front portion of the Neumann projection. You still have this one. So we could rotate this by 120 degrees counterclockwise, and we will end up with this following conformation. And this once again has a hydrogen across from the leaving group. Alright, so this is going to produce two different alkenes. And the way I like to do this is kind of to like box in the H that's going to come off, the leaving group that's also going to come off. And what you'll notice is that everything that lines up above the box is going to be on the same side of the alkene. Everything that lines up below the box is going to be on the downside or the bottom side of the alkene. The other thing too is that anything that's on the front has to be on the same side of the alkene. So notice here for these molecules, H and methyl, which will remain on the alkene, they're both on the front side of the alkene. So they're both going to have to be, in this case, on the right side of the alkene. And then the sec-butyl and the green hydrogen are on the back portion of this Neumann projection, so they have to be on the left side of the alkene. So you see the same thing happening here: methyl and hydrogen, methyl and hydrogen, sec-butyl and hydrogen, sec-butyl and hydrogen. The second thing too is that you have to be sure not to accidentally scramble the positions. Sec-butyl is next to hydrogen in the left Neumann projection, so sec-butyl has to be next to hydrogen. Over here, sec-butyl is next to methyl, so you have to make sure the sec-butyl remains next to methyl. All right, now between the two alkenes, the one that's the preferred one is the product that arises from the more stable conformer. And the most stable conformer is the one that has the methyl group anti in conformation from the biggest group, right? So on the other hand, the Neumann projection here on the right side has the two biggest groups right next to each other, and this is by default a higher energy conformation, and you're going to find it in a lesser amount in solution anyway. So the fact that this is a more stable conformation, which means that you're going to have a greater amount of this conformation present in solution, is by default allowing this alkene to be formed as the major product. And what you can see right here is that the major product is the trans alkene compared to the cis alkene that we would have gotten from this other Neumann projection. All right, so that's just from the point of view of the alpha hydrogens on this end of the molecule. But now we have to consider the alpha hydrogens on this other end. In order to do that, we have to look at the carbon-carbon single bond that contains the leaving group and the other set of alpha hydrogens. In this case, I'm going to look at it from this point of view. So the Neumann projection as it stands is basically eclipsed, right? The bromine is on top of the methyl. So what you see here is the bromine on the front is on top of the methyl on the back. Also, the ethyl, the green ethyl, is on top of the the pink ethyl, and that's what we see right here. Front ethyl on top of back ethyl. And of course, you have hydrogen pointing to the back, hydrogen pointing to the back, so they're on top of each other. So all we need to do is just rotate that so that we get the the gauge or the stagger conformation, right? So just rotate it about 60 degrees. In this case, I'm taking the back portion of the molecule, rotating it about 60 degrees so that we get the following conformation. And the reason why I want this conformation is because the carbon-bromine bond is directly across from the carbon-hydrogen bond of the back portion of the Neumann projection. So this is ready to undergo that elimination. And notice that in the back portion of the molecule, you only have one hydrogen. So this is the only Neumann projection you need to concern yourself with. Above the box that we drew in here, we're going to have ethyls next to each other. Below, we're going to have hydrogen next to methyl. And so your alkene ends up being the following. And this is the only product you expect to get from it. So comparing the two major products that you can get due to the different alpha hydrogens that you have, one of them, notice, is actually a tri-substituted alkene. You have three things bound to the alkene. The other one is a di-substituted alkene. Now, in the case where your base is small, like sodium amide, you are going to favor the formation of the most substituted alkene. This is the thermodynamic product, also known as the Zeitzev product. But if, on the other hand, you were to use a base that is considered bulky or very big, like um, um, bis, sodium bis hexamethyl disilocane amide, then in this case, and just to show you the shape of the molecule is a lot bigger than what you had before, we basically substituted two hydrogens with two trimethylsilyl groups. In this case, you're going to favor formation of the least substituted alkene. And the reason why is because when you have a big bulky base, you are going to favor attack on the site that is the least sterically encumbered. And the alpha hydrogen right here is a secondary hydrogen because it resides in a secondary carbon. But the alpha hydrogen right here is tertiary, so that's a lot more difficult to access, especially if you have a really bulky base. So you will favor attack on the secondary hydrogen. That leads to the least substituted alkene out of the two. This is the kinetic product, also known as the Hoffmann product or the Hoffmann alkene. And to kind of complete the picture, bulky alkenes, the ones that I'm most likely going to use are going to be the hexamethyl disilyl amide or diisopropyl amide, or potentially t-butoxide or trimethyl siloxide, right? So those are what I consider bulky bases. And the ones that are considered small are pretty much the ones that go and use hydrogen as a substituent or just methyl and ethyl. Those are what I consider small. Now, in the case of the alkoxides, since they only have one group bound to the oxygen, you could have isopropyl. That's still considered small. But put two isopropyls onto the same atom, like in the case of the amide, and that's already too bulky. Okay, so just be aware of these bases in terms of the size, bulky versus non-bulky, and keep an eye out for the abbreviations because most likely than not, you'll see the name or the presence of the base as an abbreviation, not as the actual, drawn out formula. Okay. To kind of finalize this process, let me show you one more example, this time using the cyclohexane rings. Notice that in this case we have two leaving groups potentially. We have the chloro group here with the dash bond, and then there's the chloro group there with a bold bond, and they're both secondary alkyl halides. Notice also that we are heating up this mixture in the presence of sodium hydroxide, which is a small strong base. So this spells out elimination, specifically a bimolecular elimination. Now, the presence of the strong base tells you that this is going to be bimolecular. All right, so what we need to do is draw that cyclohexane ring. And remember, bold bonds tell you that the substituent is above the hydrogen. dash bonds tell you that the substituent is below the hydrogen. So when we start placing our different bonds, right? So here I'm going to say that this is going to be the red bond, meaning that these substituents here, one of them has to be the pink chloro, and the chloro has to be below the hydrogen. So we just make sure the chloro is below the hydrogen. If we continue going in a counterclockwise fashion, the next substituent is methyl, and going counterclockwise here means that the methyl has to be on this carbon. Methyl also has to be below hydrogen, so that so happens that the methyl is going to be equatorial. Continuing going counterclockwise, the chloro group right here has to be above the hydrogen, and that means that we're going to place the chloro in the equatorial position. That's the only way to have it be above the hydrogen. Continuing going counterclockwise, this methyl group is above the hydrogen, so that means that the methyl group has to be on the axial position. And the final one is also above the hydrogen, so that final methyl right here has to be in the axial position. All right, now what you have to do in this case is you have to redraw the conformation so that you have the other chair conformer of cyclohexane. And the idea is that the leftmost carbon remains the leftmost carbon, the rightmost carbon remains the rightmost carbon. So all that's going to happen is that your axial bonds become equatorial, equatorial bonds become axial. And notice, however, that the position in respect to the hydrogen never changes. Chlorine is below the hydrogen on this conformer. Chlorine remains below hydrogen on this conformer. The methyl on the rightmost carbon is above the hydrogen. It still remains above the hydrogen. So you basically do the same thing. Now the carbon here, the chlorine was equatorial, now it's axial, but in both cases it's above the hydrogen. So you continue doing this until you get all the groups for the entire cyclohexane chain. And then you simply examine based on sterics, which groups are the biggest ones. And between chloro and methyl, methyl is the biggest group. So the conformer that has methyl, the most methyls position in the equatorial positions, is the more stable one. And you can see here that you have two methyls on the axial positions on this conformer, whereas on this one you only have one. So this molecule is the more stable one. And what you see is that for the more stable one, you have chlorine in the axial position, this pink chlorine, and next to it you have a hydrogen that's also in the axial position. The axial positioning is exactly what you want, because that allows you to have that anti-periplanar shape that we talked about with Neumann projections. And so the fact that this hydrogen right here is axial tells you that you're going to form this particular alkene. Notice that on the other end you do have a hydrogen, but this hydrogen is equatorial and it's not in anti-periplanar conformation. For it to be anti-periplanar, you will have to change to this conformer, which is the least stable. So you don't expect to have much more amounts of this conformer than the one here on the right side. So even though this conformer can yield an alkene, specifically the one that has the axial hydrogen next to the axial chlorine, um, the conformer right here on the right side is going to lead also to an alkene. But because this one is the more stable conformer, you expect this particular alkene to be the major product. So this is a more robust way of looking at eliminations. And yes, be aware of cyclohexane rings. You're going to have to draw the 3D structure, the chair conformation, both conformers. And once you have the conformation, you have to look for the axial leaving group next to axial hydrogen. Okay. In the next video, we're going to talk about unimolecular elimination reactions. So see you then.